and he's currently materials chemistry emeritus professor. He received his BAsc in engineering science and PhD in chemical metallurgy from the University of Toronto. And he has been an author of over 180 scientific papers and an inventor of 36 US patents. His research is currently directed towards batteries for grid-scale storage and electric vehicles, and also environmentally sound metals extraction technologies. His accomplishments include large-scale stationary storage of liquid metal batteries and the invention of liquid metal batteries, and also the molten oxide electrolysis for carbon-free metals production. He is the co-founder of 6 companies: Ambry, Boston Metal, Lunar Resources, Avanti Battery, Pure Lithium, and Sadoway Labs, and has been named as Time Magazine's 100 most influential people in the world in 2012. Online videos of his chemistry lectures hosted by MIT OpenCourseWare extend his impact on engineering education far beyond the lecture hall. TED Talk is as much about inventing inventors as it is about inventing technologies. And his talk today is going to be on mainly electrochemistry, and it's titled Towards Profitable Sustainability via Liquid Metal Molten Salt Electrochemistry. And with that, I'd like to hand it over to Professor John Sadoway.
You have a question? Can you make the screen? Oh, you have it.
Okay, so you want me speaking into this device here. I hate being spot. All right, so with that, I'm going to just press on. So pleasure to be here. The invitation of Professor Powell. I see a number of familiar faces in the audience and some other not so familiar faces, but by the end we'll all know each other. So I'm going to talk today about this topic here, and I talk about deep decarbonization. So that's what's going to happen. I'm going to give 2 vignettes. I want to make sure that I get it done on time. I really hate it when I go to a speaking event and the person goes over time. It's just so unprofessional and it's so annoying, and I never want to be that guy. So number 1 is decarbonization of manufacturing. So that means we're going to talk about steel making. And then the second one is treating intermittency of renewables. And that's going to get us into grid level storage. So those are 2 vignettes. So first one is decarbonization of manufacturing, steel making. So if you take a look at 2019, because that was the last normal year, we had some disruptive years with COVID. The world production of steel was 1.8 billion tons, 1.8 billion tons. And that's not electric arc. This is dirt to metal. This is virgin metal. And that because you produce CO2, that's the central decarbonization reaction, conversion of iron oxide, you make 3.42 gigatons of CO2. And that was 9% of total CO2, not 9% of the CO2 that comes from manufacturing. 9% of world CO2 came from steel. If steel were a country, it would be the 3rd largest. China. Number 2 is USA. Number 3 would be Republic of Steel. So that's why steel is in the crosshairs of regulators. They really are going after blast furnace and so on. So I started thinking about this back in the 1980s. Nobody cared about CO2 emissions, and people laughed at the notion that you would replace the blast furnace because it's so big, it's so efficient, it's so this and so that. And plus they said, you're stupid, Sadoway. You can't use the electron as don't use electrons. But you know, I was teaching chemistry and I didn't use DFT or anything like that. I just used some basic ideas, you know. And I knew that iron is found in nature as an oxide. It could be hematite, magnetite, And I know electron can be made sustainably. And so I put those two together, plus the big idea, first year chemistry, light dissolves light. If you have an oxide feed, you should have an oxide solvent. And so that gave me molten oxide electrolysis, because the electron is going to be a reducing agent. You don't throw a bucket of electrons in, you have to use electrodes. And that gave us the molten oxide electrolysis. And that's an extreme form of electrolysis where you're going to make oxygen as the byproduct. And that would be disruptive. And this is a cross section of the cell. So you can see you've got an anode up here and oxygen evolving. This orange zone is the molten oxide where you dissolve the iron oxide. And then by the action of electric current, you produce oxygen up here at the top, and down here at the bottom, you produce liquid iron in it, bottom, and periodically you tap and so on. And the action of electric current does two things. It drives the Faradaic processes, makes oxygen and makes liquid iron, and it generates joule. And Professor Hires was the instrumental in the upscaling, the design of this from the campus to build the first self-heating reactor that by the action of electric current alone, we were able to maintain 1650 degrees Celsius, no external heater. And this is a critical factor in this. So that was the beginning of it. And I always put not to scale, who cares? All right, and now the nice thing about this is that it's much lower capital cost than an integrated steelworks, because an integrated steelworks has a blast furnace, but it has to have coke. So they need coke ovens. You convert the coal to coke. You don't just throw iron oxide in there in any form. It has to be these centered pellets of a certain porosity. So you need a pelletizing plant. And then after that, you take the iron out, it's got very high levels of carbon, so now you have to have basic oxygen furnace. In this case, we go in once comes carbon-free liquid iron, and oxygen is the byproduct. So that's very attractive from a scalability standpoint. And, it was just cook and look. I mean, molten oxides of transition metals, they exhibit electronic conductivity. That means your Faradaic efficiency is going to be crummy. So we had a lot of challenges to tailor the oxide solvent. And then, of course, an inert anode. What are you going to make of it? You need something that can resist oxygen and be immersed in a molten oxide solvent and operate at 1600, 1700 degrees C. That was our big challenge. So put all those together and then finally you can do this. So the electrolyte design, we started with the LEM diagram. Stable oxides are at the bottom, the unstable ones are at the top. Iron is somewhere in the middle, maybe towards the top. Anything below iron will not deposit in favor of iron. So our supporting electrolyte or solvent could be silica, could be alumina, could be calcium, whatever. But this is sort of the way we started. You know, add some magnesia if you want. Then we go to ternary phase diagrams, and the purple area gives you where you've got the boundaries. You've got to be somewhere inside that zone. So otherwise you'll have the electrolyte will freeze up on you. So this is sort of the basics of electrolyte design. This is the basement of MIT. This is a molybdenum disilicide furnace. Up here at the top, you can see the cell cap with feed-throughs, electrodes coming down. The action is way, way down here. This is an alumina tube, and the alumina tube is actually acting as a light. It's white heat down at the bottom here. And so we were doing the work. This is 1600 degrees C. And now this is some visuals. This is looking down through the cap. And over here, this is the anode. In the early days, we were using platinum group metals. You'll see the thing bubbling off oxygen here. And this is a molybdenum plate, vertically disposed. Iron is forming on the molybdenum plate and dribbling down to the bottom. And this is a silicate, molten silicate. So this has got some viscosity, but you'll see there's enough fluidity that you can see things happening. You can see the bubbles coming off the anode. And this is the beginning. And of course, add external heaters because it's too small. We can't generate enough heat to compete with the radiative loss. By the way, everything that you know about how you should insulate something is wrong because your experience is at room temperature plus or minus some hundreds of degrees. So if you want to insulate batting and so on, the dominant Professor Hires knows this so well. The dominant form of heat transfer at 1600 degrees is radiation. You know how you insulate? Put a thin piece of metal and you reflect it down. So anyways, so search anode. We tried something that was viable. Well, obviously, we're not going to build a steel mill with platinum, rhodium, and iridium. So Antoine Eleanor was a postdoc with me at the time and discovered this iron chromium alloy. And it forms a surface film. You can see this is the pristine, and this is after going in for several hours. And the reason it looks so ugly is the drag out of the electrolyte. The anode is in perfect condition. And this is some of the metallography. It's a chromite surface film, and that protects and allows us to run. And this was published in Nature. And Nature, you know, it's arguably, I wouldn't even say arguably, I'm just going to say it's the premier scientific journal on planet Earth. And yet Nature publishes something in the area of extractive metallurgy maybe once in a decade. They see extractive metallurgy, this is bucket chemistry, get it out of here. You know? So for us to break through on this thing, this was really a big deal. They're really tough. They're really tough. They subject you to the most intense scrutiny. And I accept it. I accept it. You know, what doesn't kill you makes you stronger. And boy, they really take you to task. Anyways, that was published. I don't care. I have tenure. Tenure means never having to say your story. I don't care about publishing, but I do publish to launch the careers of the young people. And so there was both Antoine and Lan Yin. And because of this paper, you know, both of them, he's now a professor at MIT. He just got tenured and promoted to full professor. And she went back to China, and she's a professor at Tsinghua University, which everybody knows it's top tier university. And it's because of stuff like this. So anyways, just saying. All right, so what happened? We started a company in 2012, and it was myself, Jim Yurko, who was a student, a PhD at MIT, and Antoine Eleanor, and Professor Robert Hires was the brains behind the upscaling of it. And we designed this thing. He knew the emissivity is a function of composition at these temperatures in silicate melts, nothing. So it's a number between 0 and 1. Just pick a number, do it, run it, do a sensitivity analysis. And the very first thing that he designed, we built, and it worked. It's just unbelievable. I keep calling him out because he really did something truly amazing with that design. So we changed the name. Well, I think we originally called it Boston Electrometallurgical Corporation, which no one can pronounce, no one can spell, no one can remember. So we changed to Boston Metal. And Series A funding came from these people and Fidelity, but we also got BHP and Vale. So with BHP and Vale, that's 2/3 of the world's iron ore mining. So they're putting their confidence behind us. And this is a 10,000 ampere cell. We're up to 25,000 amperes. And this is just a little footage. This is going to tap while passing current. They're going to tap liquid iron, and then they'll pour it into molds and so on and so forth. So, you know, in aluminum and aluminum smelt, they don't tap. They siphon up the top because anybody can put a hole in the thing, but can you reseal the hole? We figured out how to do it. So we can tap on the fly and reseal and so on. Fantastic team there. So we're making better metal. It's a higher quality than blast furnace, zero emissions. Oxygen is the byproduct. And it's coming out at lower cost, unlike the hydrogen steel, which comes out at a premium of 50 to 60%. Better metal at lower cost. And I call it disruption. And I want to show you, this is one of our steel workers. This is Amanda. This is a new steel worker. This is the face of disruption. This is the new steel industry. All right, so let's go on now to renewables. I'm going to keep moving. So I like to start with this image because it shows you that electricity is tantamount to modernity. Where everything we value in our 21st century existence, you know, the phones, the computers, everything, it's predicated on the availability of electricity. And you look at this image, where you see light, you see the modern world. Where you don't see light, one of two conditions holds. Either nobody lives there or it hasn't been electrified. And if it hasn't been electrified, let me tell you, there's no more precious gift we can give the electricity. With electricity, you can participate. And it has to be sustainable. So we're not going to be instead of electricity, we're going to put electricity near the demand centers. And that means sustainable. So, sustainable, it's going to need storage because the sun doesn't shine all the time. And you say, well, the need is compelling. Why don't we have it? Because it's really, really difficult. It's much more difficult than the lithium-ion battery goes in your phone. It has to have long service lifetime, not 3 years, 5 years, like you get a new computer, new phone every so often. You don't get a new battery, just get a new phone, forget the battery. But you put something on the grid, it better last not 2, 3 years, it better last decades. And it's got to be safe. We just had Moss Landing, another lithium-ion battery fire in a 100 megawatt hour storage facility. When you try to repurpose things for purposes for which they weren't invented, you get into trouble. Pardon me. It has to be operationally flexible. It has to be able to do quick frequency regulation. It has to go long duration. The same battery has to do all of these things. You know, the battery that powers the hearing aid doesn't power the automobile, but this thing has to do everything. And it has to be super low cost. It has to be all of them. I can give you a battery that gives you the first 3, but it come in at a NASA price point. Nobody wants that. And so I made it, since cost is so important, I flipped the paradigm at the university. The university paradigm is invent the coolest chemistry and publish in a top tier journal. And maybe there's a startup company in there somewhere. Well, who cares about cost? In the startup company, that's the duty of the startup company to chase down the cost curve. But I reasoned that in this application, you're not going to get low enough. And so I said, you have to think about cost on day one. So that's why I call it cost-informed discovery. And so the path forward, use only earth-abundant elements. There's a vast swath of the periodic table that I will forbid my people to touch because stuff will not scale. You know, people work on CAD Telluride solar cells. Tellurium is about as earth-abundant as gold. It's not going to scale. I don't care that it has a higher conversion efficiency. It won't scale. So I said, you know, look at the supply chain constraints we have today. Lithium, people are getting nervous about lithium. So what's the answer? Well, that's onshore. No, it isn't. The answer is invent a battery that doesn't need cobalt, doesn't need nickel, doesn't need lithium. So I said, if you want to make something dirt cheap, you should make it out of dirt and preferably local dirt. That way you have a secure supply chain and make it easy to manufacture. Why they call it the gigafactory when they build a lithium? Because it costs $5 gigadollars. Steel works with an annual tonnage of 4 million tons a year. I get one battery plant. Wowee. Stupid. All right. So when I started thinking about grid level storage, I said, you got to think about this and pose the right question. You see the top line? Colossal cheap storage device. You don't see the word battery in there. If I put the word battery, you start thinking about something that's a right circular cylinder. And how do I make something that'll power my phone the size of this room? That's what my colleagues are all trying to do. I said, no, just colossal device. Don't bias with a form factor. And by the way, disregard the expert. If you want to get bad advice, go to the legacy battery producers. They're going to tell you that you're crazy, just as they did with me with molten oxide electrolysis. I looked outside the field for inspiration. I've already talked about molten oxide electrolysis. So since I knew some non-aqueous electrochemistry, like trafficking in big current, I said, let's look at an aluminum smelter. This is one up in Quebec. Left to right is probably about 100 feet, probably goes back about half a mile. This 500,000 amperes, 4 volts continuous. That's 2. And producing aluminum from aluminum oxide and turns dirt into metal for less than 50 cents a pound. So I looked at this thing and I said, this is a modern economic miracle. It traffics in huge currents. It's going to be cheap. If I can just teach this thing how to store electricity and then deliver it on demand, something that's big and cheap. Instead of starting with this, which is small and expensive, and make it big. And you hear all these people talk about economies of scale. You're crazy. What you're talking. All right. So, anyways, this is the invention. This is the, and you see at the top, you have a magnesium on the top, a low density liquid metal, and then a high density liquid metal antimony in the bottom. And in between, you have a molten salt. You can't have an aqueous electrolyte because you've got you want liquid metals. Why do I want liquid metals? Because charge transfer kinetics between the liquid metal and a molten salt are super fast. David Bradwell measured charge transfer kinetics of calcium chloride on molten calcium. He got 600 amps per square centimeter, not 600 milliamps. 600 amps per square centimeter was his exchange current. It's phenomenal. So what happens? What happens? On discharge, the magnesium wants to alloy with the antimony. But these three, I forgot to tell you. So the magnesium is insoluble in the salt, and the salt is insoluble in the antimony. Liquid metals and molten salts are first approximation insoluble. So they stratify like salad oil and vinegar. Separated. So now when I want to discharge, I connect the magnesium and the antimony to a load, and the magnesium wants to get to the antimony, but I just told you magnesium is insoluble in the molten salt. But magnesium is smart. Magnesium knows if it and becomes magnesium ion, the magnesium ion can go into the salt. And those two electrons, they come off up here and they go through the external circuit. And then when magnesium gets to the bottom, it alloys, it picks up the two electrons and then alloys with the antimony. So over time, the top layer gets thinner, the bottom layer gets deeper. And then when we go to charge the battery, we force current through and we electro-refine. We send the magnesium back to the top. And by the way, when the battery is discharging and the current is flowing, it generates heat, which is the threat to the lithium-ion battery. Just asking what lost landing. Right? We take that heat and trap it and use it to keep the battery at temperature. So the battery discharges for, say, 4 or 5 hours. We trap that heat, and then it sits idle. Then we charge the battery 4 or 5 hours, generate heat, trap it, and it sits idle. And by the normal use of the battery on a daily basis, it generates the heat to keep itself at temperature. We have to put some energy in to get the thing started, and after that, by cycling, and it wants to be cycled. This is not a battery that just sits there waiting in case there's a hurricane or something. No, we want this running all the time. I said the magnesium and antimony was our first, but if you go to the periodic table, you can these highly electropositive metals, and we did build some batteries. We built with magnesium, we built some with lithium, we build with sodium if you want. And right now we're here over in Marlborough, calcium. So any of these, and because by the way, I want to go global by building locally. Batteries in Africa should be built in Africa by African people using African resources. That way they become authors of their own future. And we're not shipping materials all over the planet. So maybe in Africa, instead of calcium, maybe we'll use potassium. You did good. Anyway, then positive electrode, I've shown you antimony. We also work with lead. We can work with tin, we can work with bismuth. We did lithium bismuth. Worked beautiful. We could even use zinc. There's a whole host of other elements. So that's it. And by the way, I hired anti-experts, not experts. I didn't want to talk to battery experts. I sure wasn't going to hire students who had been trained by battery experts because their brains are poisoned. They're no good. Look at these people, all these people in the figure, 20 people there. There's only 3 people in that figure that know anything about liquid metals and molten salts. And me, David Bradwell, who's back here, and Louis Ortiz. Everybody else, they didn't know any of this stuff. But they came. They're bright and they're fearless intellectually. So I say, you know, if you want to make change, don't go back to the legacy teaching. All right, and I just want to remind you that the battery begins with the professor. This is Alessandro Volta, and this is his first battery. It's a stack of coins, silver and zinc, separated by cardboard soaked in brine. And with this, and this was published in Philosophical Magazine in London in 1802, which is like the forerunner of nature. It was read into the record by Sir Humphrey Davy. And with this, we had for the first time current in motion. Right. Volta gave us not only the battery, he gave us everything we have in this room. He doesn't get enough static electricity. But you can't do anything unless the electrons are in motion. And you know, without any venture mentoring and all this other prattle from business school and so on, within 10 years of this invention, this was in commerce. Guys were already taking this idea and using it to electroplate and electroform metal in northern Italy. So Volta deserves far more attention than he gets. The other thing that Volta's invention first time was to prove the utility of a professor. Until Volta, nobody thought a professor could be of any use. But Volta showed us if a professor has some money and bright students, he or she is liable to do something that has some societal value. So I really bristle when I hear some people talk, oh, you know, academics, ivory tower. No, you think everything in here, it's the industry. All right. So we started a company. We've tested about 1,500 cells. Oh yeah, that got published in Nature too, 2014. And again, for the people that are on the list here of authors, this was career launching for them. So we started a company. I didn't want to go with the company, but David Bradwell and Louis Ortiz came and we said, we have to start a company. And I'm, you know, pristine guy from Canada. I just want to be a dutiful professor, teach, and that. And they said, look, you keep talking about science and service to society. You want to get science into society, you got to get off of campus. You got to start the company. So they persuaded me. So I said, okay, let's go. So we started the company. And this 2010, all the catchy names for battery companies were taken. So we called it the Liquid Metal Battery Corporation. It's a terrible name, but okay, we had to register it. And then we changed the name later to Ambry. I heard that Cisco Systems got its name because it was founded in San Francisco. And I said, well, I can do something with that. We invented the battery in Cambridge. So I took the word Cambridge and played with Cambridge, and I locked the front and back off of Cambridge, and there's Ambry. And I look up and Ambry.com is still available as a domain name. And I said, that's an omen. We changed the name to Ambry. Our Series A funding came from Bill Gates. Now, I told you, I'm from Canada. I wouldn't go to Bill Gates. It's rude. First year chemistry class at MIT. And I got so big, it wouldn't fit in a room. And in the early 2000s, we started putting on internet. And around about 2005, 2006, somehow Bill starts watching my chemistry book. All of them. And he starts commenting about it. And so around August of 2009, I get a note. He just stepped down as CEO of Microsoft. I get an email from a woman who says she's his executive secretary, and he's coming to Boston on the 25th of September, when I have 90 minutes to meet him. Well, I ignored the email. I thought the students had hacked into my account. I said, yeah, I got. She writes me about 10 days later and says, maybe you didn't see the email to meet with you. So I showed it to some colleagues and they said, I think this is real. So after some I sit down with him. He spends 90 minutes in my office. He talks about computers and education, distance learning, with his criticism of some of the camera shots in my lectures. And then he says, so what are you working on? And I told him about liquid metal battery. It's early days, I had no data yet. And he says, if you ever decide to spin that out, let me know. I'd be willing to put some money in it. And he did. A year later, my students, David Bradwell and Louis Ortiz, went to Bill, and he became our first investor. So I met Bill Gates not because I wrote a dynamite op-ed piece for the Wall Street Journal. I met Bill Gates because I was dutifully teaching a large service class in first-year chemistry. You know, sometimes it's karma here. You know, good things lead to good things. And then the other sponsor was Total, a big French energy giant. All right. So this is when we were working with paper, almost 5 years, 5,000 cycles, deep discharge every day would be like 13 years. And look at this is the capacity. This capacity is retaining 99% plus of initial capacity. If I put lithium ion on here, lithium ion would start here and would sink like a stone. By about 2,000 cycles, it would be down to about 70%. Well, if you're down to 70% of nameplate capacity, you can't meet your technological requirements, which means either you have to add new, you either have it on day one, or you got to add new capacity. So that's good. And this is now with calcium antimony, same thing. In fact, if you look carefully at this line, my eye tells me it's actually getting better with cycling. Okay. So this is what's going on here in Marlborough. We built this thing. It's about 1/4 of a 40-foot shipping container. This is 1 megawatt hour, weighs 15 tons. It's got its own anti-theft built into it. You can't steal this thing. Even if you hooked it up, you won't be able to drive down the road. It's too much for the road. It's only 67 watt hours per kilogram. And everybody says, oh, that's a lot lower than lithium ion. It's a stupid metric. For stationary storage, you never talk about watt hours per kilogram. There's only one metric that counts: dollars per kilowatt hour per cycle. If I gave you something that had only 40 watt hours per kilogram and had a capital cost of $10 a kilowatt hour, you'd install it. And so right now it's calcium chloride. Calcium chloride, that's the salt we throw on the highways in the winter. That's like dirt cheap. And it's priced less than lithium ion and non-flammable. You cannot make this thing burn. Lithium ion, I say there's only two kinds of lithium ion storage facilities: those that have caught fire and those that will catch fire. You know, as Clint Eastwood said, you know, take a look at that facility, and the question you got to ask yourself is, do you feel lucky? Well, do you? And it's sourced. There's no Congo, no China. It's all sourced here in North America. All right, so I'm going to end and with a little. I started with the big idea. I come to big. So this, we are going to have almost all electric future, and I'm saying that almost all industrial chemistry will become industrial electrochemistry. Anything that can be done electrochemically will be done electrochemically. And there are some things that can't be done electrochemically. They have to be heated, and instead of heating them by burning gas, we'll have to figure out a way to heat them electrically. So I think it's a bright future in electrochemistry. Bright future in electrochemistry. The world is going to be electro. That's it. So I think it's a very bright future for material science and engineering, by the way. I think it's better time than now to be in material science. And when I talk about science and service to society and cross that with profitable sustainability, I don't want to go green and go poor. That's stupid. That's stupid. People who talk like that are so weak. This is an opportunity to reinvent things better and more efficient and still be profitable. Let's have some questions. Someone should curate this, because you should never let the speaker curate the Q&A. Bad. Don't let the speaker curate the Q&A.
So anyone with any questions?
Now it's time for your questions. You know, as a teacher, one of the worst things I can say at the end of a lecture, are there any questions? Because there's two answers to that question. So I should never say, are there any questions? Instead, I say, now, let's have your questions. I invite your questions. Watch this one. Are there any questions? I look at my watch and I start to walk away. What's that? Saying, hell no, there are no questions. We're out of time, boys and girls. Yeah.
Since nobody else is there. Surface topographies characterize irregular surfaces, and one of the interesting things is that surface area. So, as we would say, right. And so one of the key questions. Are you going to refine in the scale?
Yeah, so in because you're generating gas, well, because you're generating liquid iron, in point of fact, once that first film of liquid iron occurs, the electrode electrolyte interface is liquid metal against the molten salt. And the same thing in the liquid metal battery. The electrode electrolyte interface is liquid metal, either at the top or at the bottom. But where your question does come into play is in the gas evolving electrode, because the gas is formed by taking oxide ion and by Faradaic process, turning it into oxygen neutral. And that oxygen neutral is sitting on the surface. And if the surface is micro rough, is it going to go to the high points and the low points? Probably going to go to the high points. Surface roughness can be an enabler, because if the nucleation of the oxygen bubbles is hindered, is activated, then that means that there's a voltage penalty, which means the kilowatt hours per ton of steel is higher than it ought to be. So it's a good question. And I will say at the moment, the number one problem is coming up with the chemical formulation that just doesn't get chewed up in that vicious environment. We would love to be at the point where we have to consider your question. But right now, the answer is they're not thinking about it. They're just trying to keep the lid on them. Lid on this.
Perfectly smooth surface rising.
Question, I'll pass it on to the
All
folks at Boston now.
right.
Yeah.
Correct.
And initially will be opting out. So in your case. Outer voltage.
Yeah, you're right. There's no question that by having because there are different types of, so you're right. You choose the anode, I call it the negative, and the cathode, the positive. All right, because anode and cathode are only anode and cathode on discharge. When you charge the battery, what was the anode on discharge is now the cathode. That's why real battery guys don't talk about anodes and cathodes. They talk about the negative, because the negative electrode is always negative. On discharge, it's the anode. On charge, it's the cathode, but it is always negative. All right, so anyway, so you choose the anode and cathode. Then what kind of reaction? Now in lithium-ion battery, it's an intercalation. In say lead acid, it's a chemical conversion. In sodium sulfur, sodium actually attacks sulfur and becomes sodium sulfide. So there's a plurality of reactions that occur. In liquid metal, it's alloying and dealloying, and it's a low voltage. But again, I said, I don't care. you know, to get onto the grid, you're gonna have to be up to 400, 800 volts. There is no battery that gives you that. You're gonna have to put a whole bunch of them in series anyways. You can do it with few. But again, the only metric is dollars per kilowatt hour per cycle. So I realized that this is gonna be quote unquote low, but doesn't matter because the cell is a low voltage cell, but the battery, I can give you 400 volt battery. So, yeah, and by the way, capital cost, cheap, no supply chain constraints, no ethical problems with the sourcing. Start thinking about stuff like that. Keeps you up. Okay,
Jason.
Yeah, so you. Doesn't mean that there'll be problems if its usage, is it required that it's being used all the time? Will there be problems if it's being used intermittently? Would it have like external heater or get it up?
yeah, it has a range of operation. It has to be used. Does it have to be used identically all the time? No. And if it goes into intensive use, the temperature will rise a little bit. There's no threat of explosion, volatilization, or any of that. But you're right. If the temperature gets too low, it may start to freeze. But it doesn't freeze boom like that. It freezes slowly from the outside in, and then at some point you start using it again. So, but if you really want to just let the thing sit there for months, it'll eventually freeze, and then you'll have to restart it. But this is designed to be used. It's not designed to be like a trophy or something.
I think Maya can go first and then proceed. Maya.
So what do you see as the biggest challenge?
Yeah, so we formed the company now 2022. People are saying, I gave my TED talk in 2012. You'll see all the haters, they come after me and say, where's Sadoway? You gave the TED talk, where's the battery? Yeah. Steeped in mechanical engineering. I'm not. I have the humility to say, I don't know mechanical engineering. Upscaling that thing and being able to manufacture it to like 6 Sigma quality, that's what's taken us so long. And by the way, you know, the metal on the top has a solid current collector. Metal on the bottom sits in the steel can, so it's already connected. But the metal at the top has a steel, it's like a nickel mesh that comes in from the top. Well, that nickel mesh is electronically conducting. It has to be a feed through. It has to have a hermetic seal that's dielectric that insulates it. And that thing has to be operating for years at about 500 degrees. And there's calcium in it. So there's a tiny amount of calcium vapor. You know what happens if calcium metal meets any of the ceramics that you love? It just destroys those ceramics. So to find a hermetic dielectric seal, that's taken us some time. I could give you one like that, come in at a NASA price point. So those are the kinds of things. And how do you prepare the salt? How do you prepare the metal? How do you charge this thing? Now that's one cell. How do you assemble all those cells into the battery that's in this 40-foot shipping container? Mastering all of that, that's what's taken us so long. And by the way, everything that people have done to bring the price of lithium-ion batteries down from $2,000 a kilowatt hour to almost $100 a kilowatt hour, most of that is useless. In our case, our chemistry is so different that we can take almost nothing from lithium-ion manufacturing. We've had to invent not just the electric industry, but the entire manufacturing world. Anyway, you got investors breathing down your neck and on and on and on. Supposed to train for a marathon, you're on a starvation diet. How's that supposed to work?
Or some of the electrochemical aspects of the liquid metal battery. So you mentioned the exchange current density is very high. Actual areas the operating.
So the current densities are much higher than you'll find in certain things like this thing on screen. It'll be very high. As far as efficiency goes, the Faraday efficiency is essentially 100%. Besides this saying, yeah, but he's using some of the energy to generate the heat. That's true. Efficiency is about 80%. We use about 20% of the energy to generate the heat. Yeah, I say, okay, so suppose lithium ion is 90+% with threat of fire, of course, but we don't have. It's the number one mode of stationary electricity storage. It's pumped hydro. Pumped hydro. So stores it in a reservoir, and then when you need the electricity, you let it fall back down, and you've got your on-demand hydroelectric power plant. 70%, 70. Now, I'm not saying, well, we're better than them. I'm just saying we're in the ballpark of them. Some of our batteries right now are at 80, 85%. It doesn't matter what the round trip efficiency is. Of course, you'd like to be as high as possible, but in the end, if you get round trip efficiency and you factor all of those numbers in and you get an acceptable space, suppose you generate electricity by solar at say 5 cents a kilowatt hour, but you have to put some of it into the battery and then you draw on it. By the time it goes around in and back, your electricity is now costing 15 cents a kilowatt hour. You're going to say, wow, that stings. So that's why don't be distracted. You know, the only question counts is what's the cost, dollars per kilowatt hour per cycle, and we're comfortable. And by the way, service lifetime. I mean, when you're talking 20 years and stuff like that.
Zoom audience caught the cost informed discovery meeting that you intended.